Hi guys, Buildzoid here, and today we're going to be taking a look at my RX 6900 XT Red Devil Ultimate Buildzoid Edition, which is probably the fastest air-cooled 6900 XT in the world. So let me show you some scores to sort of back up that claim, because that is a big claim to make. So first up, we have my Firestrike Ultra score. Right here, and yeah, that's on air cooling, and yep, I'm in 4th place with a 6900 XT, and the fastest 6900 XT currently on hardware bot. I've barely beat the guy under me, but he's on water cooling, so it's just like yeah, but anyway, I beat him, right, and I'm on air cooling, so because the thing is, with water cooling, it's I technically could water cool the card. I do have the ability to set that up. The thing is, actually, looking at his score, it doesn't look like it would make much of a difference to my operating temperatures because he's hitting 49 degrees Celsius and I was hitting 58. So, yeah, that's not worth the effort as far as I'm concerned. And also, if I'm going to go through all that work, then I may as well go all the way with liquid nitrogen. And the thing about the whole, well, Buildzoid, why haven't you run the card on liquid nitrogen yet? Well, you see, I bought a 6900 XT. Contrary to popular belief, Power Color didn't send this thing to me. Which actually, I'm not sure that anybody thinks Power Color sent me the card. But anyway, if you thought they did, they didn't. I bought it. I'm very upset about that because this thing has garbage input filtering. Yeah, anyway. So I bought it and I plan to spend more money on getting it into a better condition than it comes in from the factory, which is why it's already in a better condition than it comes in from the factory. From a overclocking perspective, not necessarily a reliability perspective. I don't really trust my soldering skills to not have, well, I've not yet had a capacitor fail on me due to how I've soldered it, but from reading capacitor documentation, my soldering technique is definitely not what would be considered safe for long-term use. So from a reliability perspective, I think we can say this is probably worse. But from an overclocking perspective, it's clocking better than when I first got it, even at the exact same voltage. But anyway, so yeah, Firestrike Ultra, top score on, well, yeah, top score for a 6900 XT, and I'm just on air cooling, and I do plan to take the card cold eventually. It's just that my budget needs to recover from the, damage that it has suffered from the purchase of a 6900 XT. Anyway, then Firestrike Extreme. I'm in 2nd place for Firestrike Extreme. So that's an even better result. Now, funnily enough, you can't run, I can't run Firestrike Extreme at the same settings that I can run Firestrike Ultra. Ultra runs at a higher frequency, or at least, the awkward thing is, I'm actually not sure what the readout is from 3D Mark, but in terms of the driver set, the settings in the AMD overclocking menu, I am running this at higher settings than I am running this. Now, the reason I say higher settings and not higher clocks is because, this does not reflect my experience of how stable it was at all. There is no way it was running 100 megahertz lower, because, on average, because Firestrike Extreme was very, very, it would just crash if I was running the same settings as I was running for Ultra. So I think the clock readout on Navi is just completely misleading, and should just be ignored. I wasn't looking at the clocks when I was benching it. I was literally just looking at the scores. So yeah, anyway, Firestrike Extreme is actually harder to run, at least for me. I don't know how it is for other people, but for me, definitely, Firestrike Extreme was sort of wait a minute, this can't run the same clocks that I can run for Ultra. My theory on why that happens is because the Ultra runs at lower FPS, and so the transient loading that you get from the power draw fling, because each time the card goes through a frame render cycle, different parts of the frame render cycle have different levels of power draw, so you get, the transient loading of, Firestrike Extreme happens 200 times a second, right? Because Firestrike Extreme runs at around 200 FPS, whereas Firestrike Ultra, well, Firestrike Ultra runs at around 100 FPS, much slower than Firestrike Extreme does, and actually in some parts it dips all the way down to 50 FPS. Firestrike Ultra is Firestrike at 4K, so because it runs at much lower FPS, you're going through that transient loading 50 times a second instead of 200 times a second. And my theory is the inadequate input filtering capacitor configuration on this card has much more time to recover on a 50 time, like it can deal with something that happens 50 times a second a lot more easily than it can deal with something that happens 200 times a second. So yeah, I'm currently in the process of searching for extra capacitors to put on the card, which is why I have two DigiKey tabs open. But anyway, so yeah, Firestrike Extreme second place, so that's even like a better ranked result because the 3090 is less competitive at lower resolutions to the 6900 XT, and the 6900 XT sort of loses performance as you get higher and higher resolution because the Infinity cache gets less and less efficient as the resolution gets bigger. But anyway, and then I also ran Firestrike Extreme for hardware bot. Now the funny thing is, I actually ran this score. Like I got this score before I went and also did Ultra and Extreme for the 3D Mark Hall of Fame. You might be like, why do you bench these separately? Well, the thing is, hardware bot has a different rule set from the 3D Mark Hall of Fame. So for 3D Mark Hall of Fame, you can't have like a warning like this because this is no tessellation. But on a hardware bot, that's legal just because of how the hardware bot database works. Basically, for a long time, 3D Mark couldn't detect if people were disabling tessellation. But eventually, the people who run 3D Mark decided, hey, we're like added detection for tessellation and LOD tweaks and all of that. So now, if you run 3D Mark, you have to run it with tessellation at stock, like 3D Mark settings. You can't change the tessellation settings. And you also can't modify the LOD or anything like that. You can't do any of these tweaks that you could do for hardware bot. Now, and when 3D Mark made this changeover to like detecting tessellation, they deleted all of the old scores. Like, yeah, I think they deleted basically all of the old scores because it was just like, well, we can't prove that these weren't done with tessellation disabled. Or maybe they did delete them. I'm not sure how it was handled, but basically, they chose to purge scores that would be without tessellation. The hardware bot team, however, sort of decided values the integrity of the database more so than the integrity of the scores themselves. So on hardware bot, we still get to bench no tessellation because all of the Firestrike submissions for like several years didn't run tessellation. All of the top scores were without tessellation. So instead of removing all the old top scores, it was just kind of like, we'll just keep running with no tessellation. So now, if you bench hardware bot, you disable tessellation. If you bench 3D Mark, you turn tessellation back on. Doesn't really like I really don't have a problem with it, right? Like if everybody's using the same rules, it's fine. So anyway, but yeah, so I did this run first, and this was actually at lower settings because I normally prioritize hardware bot in terms of benchmarking. Like I don't really pay attention to the 3D Mark Hall of Fame much at all. But then when I was sort of thinking about, what I want to do for this video, I was like, you know what, maybe I should run the card with tessellation turned on so people don't get confused by like, why is my Firestrike like score so big? It's like, yeah, it's because there's no tessellation in that. But anyway, and this was run at lower clocks because when I ended up running Firestrike Ultra, like this is way more GPU bound than like with a score like this, the CPU plays a bigger role than a score for Firestrike Ultra. So for Firestrike Ultra, I really needed to max the GPU in order to like, because the CPU wouldn't carry it as hard. Not that, like the next, like 4 scores below me are all actually like, yeah, the next several scores are all on 5950Xs. So it's not like I really have an unfair advantage, but yeah, here you really need, like for Ultra, you really need to push the GPU. Whereas in Extreme, the CPU can carry you a bit harder because the score is overall, like the CPU component of the score is bigger than in Ultra. But anyway, hardware bot, I got 4th place, and the 3 scores above me are all on like sub-zero cooling. Actually, I think even one of the, well, yeah, sub-zero cooling, because the score below me is like sub-ambient, because Chipsy over here is using a chiller. But yeah, and I'm on, so chiller, water cooling, though you can get chillers that go below 0. Admittedly, once you get those kinds of chillers, you're running more like antifreeze than water, but still, technically, like, yeah, like you can technically get those sub-zero. But anyway, so we have an LN2 score above me, then a phase change score, and then another LN2 score above me. So yeah, for an air-cooled card, probably the fastest one in the world. Anyway, now let's take it apart. and talk about what I've done to it. And actually, before we even start taking it apart, the most useful modification you can do to a 6900 XT is add a header to hook up a Elmore EVC2. Which the EVC2 is no longer produced, but there's like a successor model to it which has like the same functionality, and I think it's slightly cheaper, slightly smaller, something like that. Anyway, what this is it's a little controller from from Elmore Labs, and basically you just connect this to a compatible GPU, or more like compatible voltage controller. It's not specifically for GPUs. It'll talk to any voltage controller that this supports. And so the 6900 XT uses an XDP E132G5, and it also uses a IR35217. Both of those are supported by the EVC2. So we connect it over to here where there's the I2C header for the card, and then you can use this to set the voltages on the XDP E132G5 and the IR35217. And the reason why this is the most useful modification for competitive overclocking is because this thing, even on air cooling, it scales. So for the Firestrike Ultra run, I was running plus 88 millivolts VCore. So my max voltage was like approaching 1.3 volts at that point. Card was also pulling close to like GPU-Z was reporting like 500 watts of GPU power draw for graphics test 1, which that's the really, really hot one in Firestrike. So yeah, card scales. Even if you're on air cooling, it scales with voltage. So you really want an EVC. And on all of the cards that use a sort of reference style PCB, so like this is a reference style PCB as far as I'm concerned. Power Colors has added some extra phases and they stretched the VRM out a bit, but ultimately this is a reference card as far as I'm like this is basically a reference card. And then there's some cards which are literally a reference card with just like padding, like PCB padding up top and to the side and whatever. But anyway, like the thing is, a lot of the cards that use the sort of like that are based on the reference PCB, they're going to have a header, like the pads for an I2C header right here. So yeah, I just added my own little connector to that, and now I can attach the EVC to it. Technically, like other people who have run the card, like I'm not the first person to hook up the EVC to one of these cards, but most of the other people who have been running EVCs on these cards, they hook up to like the test points coming right off of the voltage controllers. So they solder wires directly to the test points, and it's just like, that's like the uncivilized way to do this, okay? Like the lovely people over at AMD gave you an undocumented, very actually hard to recognize header right here because it looks like a transistor footprint. But no, it's a header. It looks like, but yeah, but admittedly very like annoying to identify I2C header. Like use that for your connection. Like don't, especially like the main reason I don't like soldering wires to test points is that's how you rip traces out of PCBs. Whereas this is meant to have a connector attached. This isn't. Or wires or anything like that. And now, admittedly, you can glue the wires to the PCB, but now you're adding glue to your card. Like I said, uncivilized. So, yeah, that technique works fine. This is, in my opinion, way better. And what's kind of neat about the way I actually soldered this connector, you'll notice that it's like really sitting like almost flat against the PCB. It's not quite. There's a slight angle to it. If it was flat, then there's like a little SMD component that you wouldn't get past with the connector. Now, anyways, with how low this is sitting, I can actually put the backplate back on the card, and that won't touch the backplate. Like it clears under the backplate. So that's kind of just like I like to when I mod cards, like sometimes I don't care, but sometimes like I think it's always neat when you can mod a card such a way that it's impossible to tell that it's modified until you take it apart. Like if I put the backplate back on this, you can't really see any of the modifications because they're all under the backplate. There's nothing really sticking out anywhere. But yeah, that's probably going to change because I can't figure out what to do about the input filtering situation on this card. It's really quite bad. But yeah, so attach I2C header over here. Best place to do it as far as I'm concerned. And yeah, so that's super convenient. And this is like anything reference based. So like ASRock OC formula has it because it's reference based. Probably the I'll have a video about the PCB of the OC formula eventually, but yeah, so there's the Red Devil cards that use this layout. There's the Tai Chi from ASRock that also has this header. There's like a Gigabyte card that's also reference based. Like basically tons of cards have that header right over there. So best place to hook up the I2C as far as I'm concerned, because you really like don't have to worry about it too much if you hook up over here, whereas over here it's like very fiddly to do and annoying. And like I'm really surprised nobody bothered to trace this out sooner, because it's like there's a limited number of headers on this thing, right? Like we have these, which I checked those. None of those knows how I score C on them. There's this that doesn't do anything. There's this that doesn't. I don't know what that's for. I don't know what this is for. I don't know what these are for. Those aren't I2C headers. Like this would be like where you'd expect it to be because it's like near the controllers. But nah, that doesn't. I don't know what that's for either. It's not for the I2C. It's over here. But yeah. Anyway. So that's probably like the most important modification you can do. And then you just buy yourself an Elmore Labs EVC2 and bam, you get voltage control. Technically, you can also use a trimmer to skew the voltage sensing circuitry of the voltage controllers. I would strongly recommend you don't do that, but you can, and it can work, but it's a terrible idea. Like you really don't want to be doing that, but it is like it is possible. I don't recommend it. And I'm saying and I'm not going to tell you how to do it either. Like, I've done that, but I don't recommend it based on experience. So anyway, I'm not sure. Do we take the card apart now, or do we just... no. Let's not take the card apart just yet. Well, I mean, I can start on that. But zoom in a bit. So obviously the other thing, other than adding the header over here, oh, there you can see it a bit better. I've gone absolutely to town on this thing, adding capacitors just everywhere. Yeah, VCore has, so all of these capacitors over here that I added, those are 22 microfarad multilayer ceramics. I believe rated for 4 volts off the top of my head. I believe I bought like 200 of them or something. They're 0603 package size. They're awesome because 0603s, like they're very like a small, high capacitance, convenient to just jam sort of anywhere, which is why I've gone ahead and put so many of them on the card. Like they just fit. They fit really well. You don't really have to worry. Like if there's a little gap, you could probably put one. But anyway, so I added a bunch of those. Which actually didn't really achieve much of anything for VCore, at least not initially. The issue is I can't really do, like, since I have one card, I am not going to go, especially since that one card is very expensive, I am not interested in, like, putting stuff on, taking it off, and then putting it back on again for the sake of getting, like, really good test data, because, like, unless it's getting worse, I'm cool with it, right? Like, that's the thing, is just, like, so I don't know if because the thing is like initially because I did all of this first, because normally my assumption with any GPU is that you upgrade the output filtering capacitors first, and then input filtering is like not relevant. Like the vast majority of GPUs, you do stuff to the input filtering, it doesn't make a difference. This card is the anomaly in my experience, where it's like nothing happened until I added a bunch of capacitors to the input. And this is still not enough as far as I'm concerned. But anyway, so yeah, all of these 22s for VCore, I added them to VDDCI. This is VDDCI over here. I added some to 0.75 volts. Actually, I think I added just one to 0.75 volts over here. This capacitor didn't used to exist. There was an empty pad here, so I added that. That's for 0.75 volts. That was probably a total waste of time. That rail, I don't know, that rail is probably very minor, but it doesn't hurt anything to add adding caps doesn't hurt, especially when you have empty pads indicating that at some point there was meant to be caps there. And then they decided to get rid of them for cost saving reasons. But anyway, then we have the SoC rail, which I just added some more multi-layer ceramics to that, because unfortunately there wasn't any like empty bulk capacitor pads that I could have soldered more capacitors to easily. Then VCore, we have like more multi-layer ceramics on VCore up over here. I didn't do anything in this area because there's not really a lot of space to work in, so I didn't really go there. And I don't want to stack them vertically on the back of the card, because vertically stacked multi-layer ceramics have very little structural like rigidity, so they tend to break off and cause more, like they tend to cause damage. Like if you put the card down on the desk, bad. So yeah, so that's sort of what I did for the output filtering is just throw 22 microfarad multi-layer ceramics everywhere until I was bored. V-core is well in excess of like 30, having 30 of the 22s. The other rails, I don't know. Like literally, I just went like I didn't go like, hey, I'm gonna add X. I just kind of went like until I get bored. Other than that, the memory also has some extra capacitors on it, and that's like these guys. That's this right here, right? Like you can see that there's two of them right next to each other, and this is sort of inspired by NVIDIA. Because if you look at how NVIDIA does their filtering for their memory chips on their GDDR6 cards, and then you compare it to how AMD does it, um, I can't believe this actually runs. Like that's the thing. Like there's very little capacitance behind the memory chips on a AMD GPU compared to an NVIDIA GPU. And so one of my theories for why these cards are so bad at memory overclocking is just like there's not enough filtering for the memory. Um, and so that's why I added all of these. These are 0402 4.7 microfarad multi-layer ceramics, and I added four of them to each memory chip. Right, so you have one, two, three, four, and I did that for every single memory chip. I also added some 22s to the memory rail, but those are on the front of the card because there's not really anywhere to put them on the back of the card. And I also added some 470 microfarad polymers to the memory rail as well. And I'd say that's responsible for my ability to bench this card at 2180 memory. At lower core frequencies, I was actually getting like decent, like proper memory performance all the way up to like 2200 megahertz. But I assume as the core gets faster, the load on the memory controller increases so much that the memory stability gets worse. And the thing with the Navi cards is that as the memory stability gets worse, you initially lose performance. You don't initially get artifacting, you just start losing performance. Which, yeah, I'm not sure how that works. Like, some people say it's ECC, but I don't believe it because if you keep pushing the frequency high enough, eventually you start getting artifacting, and then, like, full on just crashes and just, yeah. So, like, these cards generally don't artifact, but you can get them to artifact. You definitely can. So, I'm not really, like, I think. Like looking at some of the software monitoring utilities for the clock speeds on these cards, it kind of looks like the cards have dynamic memory clocks as well. I'd love, like, I really wish I had an AMD contact so that I could confirm that, but it looks like these have dynamic memory clocks. So maybe when you push the memory clock too high, and it starts getting unstable, it starts like throttling the memory clock really hard, which would explain why you don't actually see any artifacts but lose a bunch of performance out of just nowhere. And it is a lot of performance. So like I think the card starts like aggressively underclocking the memory. Like it might start aggressive, like the clock might hit a like peak frequency, get unstable, get downclocked, like way more than necessary. You lose a bunch of performance to that, and then it brings back up to peak frequency, which is why eventually you can still get it to crash, right? Because if there was errors getting corrected, then it'd be like even at high frequencies, you would assume that it wouldn't let errors just pass through into the render output, or like completely drop the render output, which I had happen on one occasion. Like before all of the capacitors, what was kind of funny is like you could get the card to actually run benchmarks without rendering anything if you just clock the memory high enough. It would still, the FPS wouldn't go through the roof, so evidently the core was still processing some kind of data. It was just never like passing it to the display output, so you never got to see it. So that was kind of fun. You can also get that effect on like 290Xs if you push them really really hard. And actually, a lot of AMD GPUs will actually just do this thing where if you keep pushing, like if you push them far enough, they'll just stop rendering whatever the hell they're supposed to be rendering. So you'll just get a black screen, and you'll probably still have an FPS counter, which is really interesting. I guess 2D elements somehow don't get affected by it, like the 3D part. Like the 3D part doesn't get handed off to the render out, like to the display output, but the 2D stuff does. So you still get like an FPS indicator, but it's just a black screen with an FPS indicator. And you can still, and from the FPS indicator, you can tell like evidently it's not like bugged out and not rendering anything because the FPS doesn't shoot through the roof. It's just, yeah. So anyway, the memory overclocking situation is interesting, but my card, like for benching, I like all of my top scores are at 2180 on the memory. Which is the highest memory clock I've seen anybody bench one of these with and actually still get good scores. Like I can go up to 2200 without crashing. Well, sometimes without crashing. That's the funny thing is like 2200 sometimes takes out the drivers and sometimes it doesn't. But yeah, I can sometimes like if I go up to 2200, it'll definitely perform badly unless I'm at like low core clocks. So yeah, it like the memory situation on these is interesting, but yeah, so I'd say the caps are mostly responsible for my ability to bench 2180. I also messed around with like more memory voltage and less memory voltage and more memory controller voltage, less memory controller voltage, and it doesn't really seem to do anything. In fact, I ended up running some of my Firestrike runs with undervolted memory just to see if it like does anything to the memory stability. It doesn't. You can undervolt the memory and it still runs the same clocks, and it doesn't like lose performance or anything, so super weird. Same goes for the memory controller. Like I ended up just running the memory controller at a fixed 0.8 volts instead of leaving it on the dynamic voltage mode where like at idle it would sit at 0.7 and then ramp up to like 0.85. I would just run it at 0.8. But anyway, yeah, so the only thing that really seems to like make these cards, well, on air cooling at least, the only thing that really seems to be worth doing is just mash the V core, and that'll make it run higher clocks just fine. So that's how I got the really high clocks that I'm getting. It's entirely just lots and well, it's not even a ton of V core. It's like like, I think I was all the way up to plus 88 millivolts. And what's interesting, at plus 88 millivolts has finally started to get some artifacting. So evidently, like, well, yeah, so you can get even the core to artifact, which is interesting because before, at lower voltages, the core would never artifact. It would just crash. So yeah, these cards are kind of interesting to mess with. Very different from what I'm used to, where it's just like, okay, now it's artifacting, but the performance keeps going up. Now it's artifacting more, but the performance keeps going up, and now it doesn't run anymore. Right? That's the usual expectations for most GPUs for me, and this doesn't do that at all. This will quite happily look like it's perfectly stable and then just drop. And sometimes it'll like reset the whole system, and sometimes it won't, which is kind of interesting. Yeah, but anyway, the other modification that I did, and that made the most difference to the overclocking on this card, is not all the output filtering capacitors. Well, I'm not sure. Maybe, like, the thing is, the output filtering capacitors might have been made significantly more effective by the input filtering modifications that I did. So you see all of these big capacitors, and then also these guys over here, which you can also see, on the other side of the card as well. Those are the input filter, like the large input filtering multi-layer ceramic capacitors from an RX Vega. Yeah, and adding all of those, even at stock clocks, stock volts, made the card clock like 20 megahertz higher. Now, the problem is I added these after I did all of the output filtering stuff. So, or at least like 90% of the output filtering stuff. And then I did the input filtering, and then the card started to clock higher, and that was, and the annoying thing with this is like, so I don't know if like if these played into the effects of the input output filtering, or if doing the input filtering upgrades alone might not do anything. You might need both input and output filtering upgrades in order to get the effect that I got. But yeah, like the input filter, like, because without the input filtering, the card just didn't seem to, well, the memory improved, but everything else was just kind of like the core wasn't getting better or anything like that. And then I added all of these input filtering caps, and suddenly I can run, I was benching like 2850 max on stock vaults. Like, what? And by stock volts, I mean the voltage slider maxed out at 1.2 volts. Because like when you enable the voltage slider or advanced mode or whatever the hell it's called, when you enable the voltage slider, it defaults to 1.2 volts. So I consider that stock, okay? Because it defaults to that. But anyway, yeah, so I could go all the way, whereas before all of the input filtering mods, I could only bench like 2820 max clock. So I could bench 2820, and then after the input filtering mods, which, after the input and output, because the output stuff was already there, I could suddenly bench 2850. Or at least, like, 2850 was a bit temperamental, it wouldn't always pass, but 2844 was, like, perfectly stable, which was like, whoa. the input filtering on this thing sucks. And it really does. If you compare the input filtering capacitor configuration of this thing to like older AMD GPUs, like you need to go all the way back to like mid-range cards from 10 years ago in order to find cards with less input filtering than this does. Than this has. And I don't really, well, no, I do fault Power Color for that, and I also fault AMD for that, because Power Color took the reference AMD design, and they stretched it, and they didn't do anything to the input filtering. They didn't improve it in any way, shape, or form. They didn't upgrade it, they didn't like downgrade it or upgrade it, they just didn't touch it. They just kept it exactly the same, and then, well, I guess you could say they added extra multilayer ceramics, but that's because each phase has to have its own high frequency, capacitors like right next to it so that they function. So I don't really count these. Like the multilayer ceramics that the cards came with for input filtering, I don't count those. You don't really have a choice with those. You can't not have those as far as I'm concerned. And anyway, so yeah, throwing a bunch of capacitors from a Vega on the input filter made the card clock significantly better. But it gets worse. Believe it or not, because after the run-in with the sort of like, whoa, adding a bunch of multilayer ceramics from a Vega makes this card clock better. I wonder if the bulk capacitant, like the bulk input filtering capacitance, is also that bad, and it turns out it is. So go on to this image right here. Give me a second. There, see that? So this is a configuration of the card that obviously is no longer, like, I took that off. Which the problem with that configuration is those caps are gigantic. They are 10 millimeters in diameter, and I don't want them on the back of my 1800 quid card. They're way too big. There's also not really anywhere to attach them properly, so right there, they're just kind of hanging off of the multilayer ceramics, which is just super sketchy. If you grab the card wrong, or you like forget about it and put something on top of it, you're probably gonna break the like tabs off of a multilayer ceramic with doing that, with caps that big attached to them. So that right there is totally not okay. Now, you could admittedly like glue them to the card, which would kind of reduce the risk, because again, like the issue is like you'd still have the option, like I guess depends how hard the glue is. But if the glue is kind of gummy, you still have like the torque, like you could still torque the caps relative to the multilayer ceramic, and it's just like so they wouldn't necessarily come off completely, but they would still be able to apply enough leverage to the caps that they're attached to cause damage. So that definitely just not a viable config. Like that is not a configuration of the card that I want to have. It totally works. So that further, like, that didn't have as much of an impact as the Vega caps, or at least I didn't test it that much, but it slightly helped with core overclocking again. But the crazy thing about doing this was that it massively reduced the coil whine, which was not something I was expecting whatsoever. Like, that wasn't even what I was testing for. I just noticed, whoa, the card is, like, way quieter than I'm used to, and then it's like, oh, right. Because, yeah, this thing has a bunch of coil whine, and all of the coil whine, as far as I can tell, is probably from the input filtering inductors. And so, yeah, if you add a bunch of extra capacitance to the input filter on the output side of the input, on the, like, VRM side of the input filtering inductors, then the voltage swing, like in front, like the voltage difference across those inductors is going to get smaller. Therefore, the like current flow, like the changes in the current flow through those inductors is also going to get smaller. Therefore, the change in the magnetic field of them is going to get smaller. Therefore, they're going to vibrate less. Therefore, they're not going to make as much noise. So, like, yeah, it makes perfect sense that this would reduce coil whine. It's not what I was aiming for, but neat. It makes less coil whine. Anyway, these caps are 30 microfarads each with a 7 milliohm ESR, and they're way too damn big. So I took them back off again. But that right there is kind of like... So basically, after doing that test, because the reason I did that test was like, I already initially had a suspicion that the input filtering, like after the multi-layer ceramics from the Vega, I was like, oh, okay, so the input filtering on this is evidently quite bad. I wonder if not only is it lacking in the multi-layer, like in the high frequency stuff, and I don't even know that it was lacking in the high frequency stuff, because yeah, I added a bunch of multi-layer ceramics, but I also added a bunch of them. So there's a decent chance that the improvement was just from the extra capacitance alone rather than the reduction in impedance that a bunch of extra multi-layer ceramics in parallel would offer. Yeah, so just adding a bunch of capacitance on its own might have been the benefit. So I wanted to run an experiment. Would more capacitance make the card better? Like a lot more capacitance make the card better. And yeah, it does. Slightly better overclocking, much less coil whine. And when I say slightly better overclocking, like we're talking like 10 megahertz. So not really like from the factory, I guess the biggest, like if you were a regular consumer, I guess you'd be very excited to have less coil whine. From my perspective, it's kind of like, not really that much of a difference. Um, but Yeah, so that is why I've been searching for more appropriate capacitors for doing that with. And unfortunately, high voltage capacitors, um, and when I say high voltage, I mean like 16 volts because it's an ATX power supply that outputs 12 volts. Everything, like if it's not like what I consider everything everything that goes into a VRM is high voltage instead of, output of the VRM, low voltage, input of the VRM, high voltage. And technically, I do know there's boost converters, but anyway, so for input filtering, which is, a 12 volt, like input power for a GPU is 12 volts. You need to use 16 volt capacitors because you can't really get like if they made 14s, which they don't, you could use 14s, but you can't so 16 volt capacitors. The problem with 16 volt capacitors is that relative to their, capacitance and ESR, they are very expensive, like 270 microfarads, 16 volts, 8 milliohms of ESR. And this is 5,000 hours at 105 degrees rated. And one of them is a pound. And this is honestly not that bad. This is the cheap option. No, the expensive option is this. And this isn't even the really expensive option. This is just sort of the expensive option I'd be willing to tolerate. Because these guys are 50 milliohms ESR. These are tantalum polymers. Yeah, see? Aluminum polymers, tantalum polymers. So these have 50 milliohms of ESR, 16 volts. 1,000 hours at 125 degrees, so probably equivalent to 5,000 hours at 105, or similar to that. I'm not sure how that works out exactly. And the thing is, these are 1.5 pounds, but they only have 100 microfarads of capacitance. So in order to reach, so if I just need, because the 330s I used, I added 6 of them. So that was just under 2,000 microfarads extra. So if I need 2,000 microfarads, it's going to cost me 22 quid in freaking tantalums. Or in these, it's going to cost me a lot less because these are 270 microfarads, so I only need 10 of them. And actually 10 of them would already be kind of way more than 10 of these is more capacitance than 20 of these. That would be 27 of these. But yeah, the thing is, I've not yet made up my mind because, obviously these are way more cost effective, and also I think the lower ESR is better. And I just generally, because my theory, because the coil whine happens at the frequency of the frame rate, so I really think that the tantalums have a high frequency high frequency impedance advantage, which you can't see it from the ESR, and it mostly kicks in once you start approaching the megahertz range rather than 100 kilohertz. But the thing is, I don't really think the problem here is filtering out things that happen at 100 kilohertz, because you're rendering 200 frames a second, which is 200 hertz, right? So I don't really, I'm not too concerned about the super high frequency performance. And, through-hole polymers like this are still good to the 100 kilohertz range just fine, or 200 kilohertz, something like that. So I'm not too worried about, so I'm not really so the whole oh, these are amazing at super high frequencies is this is not really what I'm looking for here. The problem, so you might be wait, why are you even considering the tantalums? Well, the thing is, these are 6.3 millimeters in diameter. So you know, going back to the whole, oh, my I2C header fits under the stock backplate. None of these don't. These very much don't. There's 4.3 millimeters by my measurements. There's like 4.3 millimeters of clearance under the backplate. So I can't have 6.3 millimeter caps. They're 2 millimeters too big. Whereas the tantalums, these are only 2 millimeters in height. So these would totally fit, but they're also really expensive and probably kind of trash, in terms of, well, not necessarily trash, but I think they probably deliver worse performance. And so, yeah, I'm really annoyed about like the layout of the PCB because or more like arguably the heatsink design as well. Though, to be fair, the heatsink works really well. Like, I was pushing a ton of power into the card, and the heatsink dealt with it like a champ. But the thing is, like, the design of the heatsink on this card really doesn't leave any space for mods. If we zoom out, we're going to take it apart now, and I've replaced one of the thermal pads ended up getting absolutely shredded when I was cleaning all the, well, you know, all of these caps I used, well, when adding all of these caps, obviously I was using flux. And when I wanted to clean all the flux off, well, I needed to get all the thermal pads off of the card and, you know, away so that I could clean the flux off with alcohol, which would probably destroy the thermal pads. And so in the process of removing the VRM thermal pad, I absolutely just destroyed it. It's a very, like, Power Color uses some really nice thermal pads. Like, they're really soft and they probably have a really high thermal conductivity. The downside to high-end thermal pads is that they're also just, like, approaching the consistency of thermal paste. So they just disintegrate if you mishandle them. And so those are all gone. So, like, one of the VRMs just doesn't have thermal pads anymore. It's on thermal putty now. So yeah, that's what thermal putty looks like. It's the white stuff. So that's going to take a while to like reapply, I guess. Works fine though. Also, Cryonaut Cryonaut Extreme edition for the thermal paste on the core works really well. Though I'd say you really like this is more like this paste is like it's really expensive. I think if you're using this on like water cooling or something, you're spending spending money for no. You're spending way more on thermal paste than you really need to, in my opinion. For extreme overclocking, however, it's basically a must. And Der Bauer sent me a ton of it. So yeah, I just kind of ran it on air cooling because it's like the best thermal paste I have. So, you know, may as well. When pushing the card to its very limits. But the problem with this heatsink is that there's no space, right? Like, because it's like, okay, so I want to add like if I wanted to add extra input filtering capacitors, I want them over here, and I want them over here, right? Like in this area. That's all heatsink. There's zero space for extra capacitors in that area, right? So that's sort of my main complaint, and the same goes for the same issue. Like we have this part right here, which I guess I could like run pretty long lead. Well, yeah, no, there's just no space, right? Like that's the whole like there's really no space for putting caps on this side of the card, which I'm kind of annoyed about because there's other cards in the past where I've managed to sneak like a lot of capacitors under the heatsink, and then this heatsink is just like it is. Like Power Color basically went like, okay, so we're gonna measure the PCB, and then we're gonna occupy all of the empty space above it with fin stack, and it's like, well, it is a really good heatsink. It can deal with so much heat. I really wish there was more space for capacitors under it though. Anyway, yeah, so here's the card, right, from the front. And of course you'll probably, you can't really tell from this angle, but Actually, you can't really tell whatsoever. But anyway, even on the front, so obviously I added a bunch of multi-layer ceramics to the back. I also added a bunch to the front. I can't help myself. I see I'm bored, I add caps to a card. Oh yeah, and then this is the extra bulk capacitance for the memory VRM. This one doesn't normally exist. This one, like, basically every 6900 XT is missing a capacitor from its memory filter. So I put that back, and then I put these two over as extra. And you can see these are attached with wires because... well, the thing is, like, there's no point desoldering the existing capacitors as far as I'm concerned. They're SMD, so they're perfectly good. Like, they're not Panasonics, they're APAC, but I don't think that's going to make too much of a difference in terms of performance. Like, I don't really... Like, a lot of people do, like, capacitor replacement on motherboards and stuff, and I'm more in the camp of capacitor addition, okay? Because more caps in parallel is better than less caps in parallel. You get less ESR, less ESL, and more capacitance. Like, what could possibly go wrong? Until it tries to turn on and trips short circuit protection, which you need to go really far in order to get to that point. And anyway, so yeah, so I just sort of added those two and then had to use wires because there wasn't really any other way to attach those. But honestly, like, this, in my experience, this, like, as suboptimal as doing this, really on paper this should be really bad. In practice, I've not really noticed it causing many issues. Other than that, I've added multi-layer ceramics to the VDD. Well, I added a multi-layer ceramic over here to VDDCI, and then we have VCore, 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 more VCore over here, and more VCore over here. You might be like, why did you leave out these three capacitors? And it's because, like, these memory chips are in the way, and I didn't really feel like accidentally resting my... Like, it wouldn't... Like, in my experience, it's not really going... Like, I've not had a card with dead memory. Okay, like, or I've never killed memory chips. Memory chips are tough, generally speaking, in my experience. But yeah, I prefer not to expose them to unnecessary heat, so I just kind of avoided those. Then for memory, we have extra capacitance here, and those are the 22 microfarads, and here, and here, and there, and there. Unfortunately, the card really isn't designed very, yeah, the card really isn't designed to have more capacitance than it comes with from the factory, so finding locations to add capacitors was really annoying. And then also more capacitance on VCore over there. This is the 0.75 volt rail, 1.8 volt rail, VDDCI, memory, VCore. These two phases are SOC. Oh yeah, and there's a secondary 1.8 volts, and I'm not entirely sure that this is an LDO, but I think it's an LDO, and this is 1.8 volts for the memory. Anyway, yeah, so input filtering. These are the coil wine production inductors. These are, as far as I can tell, this is where basically all of the coil wine comes from. It's these two guys over here. And then the input filtering, in terms of bulk capacitance, is... I'm actually not entirely sure that this is input filtering. It might be. I hope it is. Because if it isn't, then this is so much worse. But it's basically these four caps and this one. And it's like... And also, these are 180 microfarads each. So... This has, for all intents and purposes, no input filtering capacitance. And what little capacitance there is not even really laid out that well, because it's like, this is the thing you're filtering. This is where you put the filter for it. Really. Now, admittedly, these are, polymer capacitors, so they're not meant to deal with high frequency stuff, and putting them this far away on the PCB probably doesn't really make that much of a difference. But, like... Why are there so few of them, and why are they so small? And like, because the thing is like, if you compare this to a Vega will have a 150 microfarad tantalum polymer capacitor per phase. This has 6 on the entire bloody card, and I'm not entirely sure this one's actually for, like, the VRM over here. It might be part of the 5-volt circuit over there. Like, the 5-volt regulator over here. So it's like... yeah, this is just hugely disappointing to me, because if this used the same input filtering, like, design style as what you see on a Vega GPU, you would have a tantalum polymer capacitor for every single phase. There'd be a tantal, like you'd have one here, you'd have them, like every single phase would get its own bulk capacitor. And then there's this thing where it's like you've got these four and this and that. Like, I like, and it evidently like isn't optimal, right? Like, because it did, like the card does clock better when you add more input filtering. So it's just like, yeah. So this definitely, well, to be fair, at stock it's fine, but like this is an 1,800 quid custom custom PCB RX 6900 XT. It really is just a stretched reference card. There's not really, like, the thing is, there's not that much you could really do to an AMD GPU to make it massively better compared to, yeah, you take like, what I would do if I was doing this is, like, I'd take the reference PCB, I'd stretch it like Power Color did, and then I'd add more input filtering capacitors. Maybe I'd even add them over here. I'm pretty sure you don't actually have to have them directly off of the VRM. Theoretically, it should be a bit better. If you want a very nice example of like distributing your bulk input filtering capacitors, look at like Asus and Gigabyte motherboards. Well, new Gigabyte motherboards. Old Gigabyte motherboards didn't believe in that, but new Gigabyte motherboards are a great example of that. Asus motherboards for many, many years, like you basically had not necessarily that many capacitors, but you did, like, the capacitors that there were basically evenly distributed among the phases around the 12-volt power plane. And then there's this thing where it's like, so this is where our power delivery, there's our filter. It's like, yeah, I have no idea why this doesn't work that well. Real mystery. RX, like, well, I didn't prepare an image for this, but I think, like, I want to drive the point home because I'm annoyed with this. I'm extremely annoyed. I paid 1,800 quid for this thing, and they couldn't be bothered to put $20 worth of capacitors on it. And also, like, when I say 20, actually, if they put $20, the funny thing is you can't compare the DigiKey prices that I'm seeing to what, like, Power Color would be paying if Power Color actually decided to design a proper output, like proper input filter for this card. So first thing because the thing is I'm paying like not bulk, right? Because I'm buying like 1 or 20 capacitors, so I'm not paying bulk prices. And I'm also buying them from DigiKey. I'm not buying them directly from the manufacturer. And DigiKey, and there's distributors that are much cheaper than DigiKey. So you wouldn't even have to go directly to the manufacturer to get a price. You just need to go to a distributor that sells them in, like, 1,000, like 10,000 units at a time or something like that. Just much larger volume than what, like, you'd be buying from DigiKey normally. So, like, if Power Color put if I put $20 worth of capacitors on here, it's like less than what $20 of capacitors would do if they were being applied during the actual manufacturing process of the card. So yeah, I'm pretty annoyed. Especially since, like, this is the first time I run into a card where adding input filtering capacitance actually makes a difference. Okay? Because normally it doesn't. And I guess that makes sense when historically AMD GPUs would look like this. See this? Look, like, we're going to get the full-size image so we can zoom in on them. Like, there's our input filtering inductors, right, over here, right? So, wait, okay, well, there's your input filtering capacitors. Those are 150 microfarads each. And there is one for every single phase. Even the HBM power phase has its own input filtering capacitor, which I think is really excessive because, like, the HBM doesn't really, like, at least I don't think it goes through as, like, violent transient load cycles as, like, the rest of the damn card does. But, like, this is an input filter. What Navi comes with is a bloody joke by comparison. Like, let's like, I'm gonna pull up a card which has, like, an equivalent, like a similar input filter to what you get on a Navi card. Okay. Now, admittedly, this has a lot less ceramic on it, but 1, 2, 3, 4, 5 bulk capacitors for input filtering. So yeah, that's kind of approaching like the 6 that you get on Navi. And this is an R7 260X. It's got a single 6-pin power connector. And I think actually these capacitors are higher capacitance. These are 270 microfarads each. So this has more input filtering capacitance than a Navi. Than a big Navi card. Like, AMD, what the hell happened? Alright, let's pull up a reference 7870. Because I think this is a 5-phase V-core. And, oops. Nope. Oh wait, this is the 7850. I clicked on the wrong image. There we go. So this is a 7870. So you've got 4 bulk capacitors over there for input filtering. You've got 2 more over here. Are they? They should be. The marker, oh yeah, so 16 volts. I was looking at the wrong end of the capacitor for the voltage rating. Yeah, so these are 16 volts as well. There's our input filtering inductor. And that's just like right around the V-Core VRM. And this is a freaking 7870. Another card that comes with two 6-pins. Okay, I was like the single, it's not, it's 2 6-pins, but not much of a difference. And then you've got like on the bottom edge, I think for the memory, yeah, you've got 2 more 16-volt capacitors for the 1-phase memory power, and then another 16-volt capacitor for what I was assuming is the like VDDCI for the card. Actually, I'm not sure which one of those is which, but anyway, you get the point, okay? Like, how the hell do mid-range cards from 10 years ago have better input filtering than a modern flagship that pulls like twice as much power? Okay, like that's the thing is like when I was benching this thing, like at stock, like the stock, actually, yeah, even the stock power limit on this is like twice the power of a 7870, because I believe the 7870 had a 150 watt power limit or something like that. And so this pulls twice the freaking power, and it has less input filtering. Like, what? Like, how does that make any sense? Vega had a perfectly good input filter. The 7970, 290X, Fiji, this is like even Nvidia cards, you can't complain about the input filtering configuration on them. Not even like historically. Like it used to be like like old Nvidia cards had really garbage power delivery, but the capacitor configuration was still fine. And then we have this thing where it's like, okay, so we've spent, we have 70 amp smart power stages. We've got these super high-end voltage controllers from International Rectifier. One of them can does 14-phase V-core without doublers and 2-phase SOC at the same time. And then you just don't put any input filtering capacitors. And it was like, but like, it's not like they ran out of space, right? Like I had enough space to put my signature on the stupid thing. So there's evidently plenty of space. Just like, yeah, like filtering, who needs that? Yeah, like GPUs don't have power transients. GPUs don't pull different amounts of power, in different parts of the frame render cycle. Especially not modern ones with their crazy advanced boost algorithms so that you can really maximize opportunistically peak power consumption, because that's the thing with really aggressive boost algorithm. What your goal is to basically burn as much power when you really need it and then back off of it for the rest of the workload when as much as possible. And so modern GPUs are actually even worse in terms of like transient loading on the input side compared to old GPUs. And it's like, yeah, we don't need input filtering capacitors. Absolutely not necessary whatsoever. And I've just realized this video is an hour long, but you know what? I think that's a good length. That's a good point to stop. So yeah, this card. So basically, I have mixed feelings about the card. VRM is solid. You know, like the VRM is solid. The output filtering. The thing is like when I measured this card on an oscilloscope, basically every single voltage rail looked really, really noisy. I've not yet measured it in its most recent, configuration. Um, but yeah, in some of the like when I was first measuring it, it was very noisy, and I'm starting to wonder if like maybe it was really noisy because like the voltage every time the card went through a transient, the input voltage would dip so hard that it was just like, well, the output can't do anything about the voltage dipping if there's no energy to pull in from from the input side, right? Because so yeah, it's like and it's just like I can't believe this is a thing on an 1800 quid card that pulls 300 watts. That's made by AMD. Like I don't even get why the reference design is so bad in the input filtering department. Like I don't get it. Like maybe the design maybe the assumption was that hey, we're going to just run the card at like the 300 watt power limit, and if it never goes above the 300 watt power limit, well it's going to be so power limited that the peak power draw is never actually going to get that high. Right? Like it'll just always be power throttling to be almost constantly at 300 watts. But I'm pretty sure there's some oscilloscope measurements of the power draw of these cards, and they don't do that. So again, it's just like, where did the input filter go? Why does this look like why does this look like a 7/8 not even a 7/870, right? Like really, like not even a 7/870. Um so yeah, there. I'm honestly pretty annoyed. Like there are some 6900 XTs that fix my complaint about the input filtering, but there's a lot of cards that also just take the reference design from AMD and stretch it. And this is one really good example of that. And I am not impressed. Like VRM efficiency is good. Power handling, like the amount of current the VR, like in sustained loads, this VRM configuration is actually completely fine. But the thing is, like, there's transients. This does not work for transients. There's not enough capacitance here. So, yeah, anyway, that's it for the video, I guess. Thanks for watching, and also huge thanks to all of the patrons and like supporters of the channel, because yeah, without you guys, I wouldn't be able to buy one of these in order to measure and test that it's actually way more like that. It's honestly kind of disappointing, you know? Like, it's not bad, just disappointing. My standards might be too high, but I feel like when I'm comparing your PCB against a Vega, I shouldn't have to be complaining about it. Right? Like, it's like, this doesn't even compare to a bloody Vega in terms of, like, this has better power efficiency. It's not better filtering. And that's, like, pretty disappointing. And I guess somebody might be wondering, why don't you just pull the tantalums off of the dead Vegas you have? Well, the thing about pulling tantalums off of dead Vegas is that I'm pretty sure I burn the shit out of those caps every time I try to do that. And I don't really want to be attaching burnt tantalum. Like, if you damage a tantalum capacitor, they have a tendency to explode. So I am not attaching those to a card if I don't trust them 110%. And I don't trust them 110%. In fact, I trust them like 50%. So yeah, they're not going on my card. Not on this one. They're going on other stuff, maybe, but definitely not on this thing. So yeah, anyway, there. That is now actually it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comments section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. If you check that out, it would be much appreciated, because this thing's expensive, yo. And then there's also the HOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. There's a link to that down in the description below as well. So it would be much appreciated if you would check that out. And yeah, that's it for the video. Thanks for watching, and goodbye.